So question 2 says 3 moles of N2O4 is placed in a 0.5 liter container and allowed to reach equilibrium according to the following reaction. What is the equilibrium concentration of NO2 given KEQ for the reaction is 6 times 10 to the minus 6. So we were told the equation currently sits at equilibrium, allowing us to write out its KEQ expression. It is usually expressed as the products over the reactants with coefficients acting as exponents in the expression. So we get KQ equals concentration of NO2 equilibrium to over the reactants. Now that we have this set in place, let's see if we can develop the N2O4 further. So we want the starting concentration for our ultimate KEQ formula. So the question then provides us with 3 moles at the start of the reaction in half a liter container, and you can see that over here. So if we divide the moles by the liters, we get the concentration. So if you remember that. Molarity actually equals 3 moles for 0.5 liters should equal around 6 moles of N2O4 at the start. So that's great. However, we still need to adjust the amount of reactants that will be destroyed in the reaction, and since we cannot determine this directly, we will denote it with an X. Sorry. And since this is actually taken away from our reactants, the expression will be 6 minus X. This will actually dictate the equilibrium concentration of our reactants. And so in addition, just as we cannot determine the amount of reactants that will be destroyed, we cannot determine the same amount of products that will be created. So we can also denote it with the same variable, yet since the stoichiometry gives NO2 on the product side an extra 2, it will exist as 2x. So NO2 here actually equal 2x. Funny enough, we actually have all our variables which we can plug into our ultimate KEQ formula that we made earlier. We actually have KEQ here as well, just shown in the question stem. We should get 6 times 10 minus 6 equals 2. Good. So one thing to note here is that conceptually speaking, a 6 molar solution is too high in concentration to have any conceivable change in the reaction while maintaining equilibrium. So the balance within the reaction would be knocked out of proportion. As such, it is common practice in chemistry to remove the X value for the N2O4 variable. So for a number this high, it would be common to see a rearrangement like this. And it also makes the math much easier. You can continue solving for X in this case. So this value is great to have, and it's key that we look back at what the x value means and what the question asks, as it may be a while since we have reviewed our intentions. So looking back, it becomes clear that x represents the equilibrium concentration of N2O4. The initial question asks us to find the concentration of NO2, which when looking at our KEQ is 2x. We multiply our value by 2 and get our final value. And this is our final equilibrium concentration.